Hello, thank you for being here, and thanks to the organizers of the Iberoamerican meeting on geometry, mechanics, and control in its 7th edition. My name is Javier Vega, and I'll be presenting this talk about quantization schemes. It's intended to be a panoramic view of these quantization programs of mathematics, and I'll be mostly talking about geometry quantization and deformation quantization to compare them with the paradigm in physics, which is canonical quantization, and at the end I'm going to make brief comments on the concept of quantum topological space in the sense of non-commutative geometry. Well, let's start. And the history of quantization starts in physics, of course. For physicists, the process of quantization has an ontological meaning, of course, and well, it's basically this mathematically describe the subatomic particles, the systems of subatomic particles in such a way it agrees with experimental data, and of course it does not contradict any classical description of physics. And not only this, but the physicists enjoyed recovering classical concepts and properties from their quantum nature in pretty much the same fashion thermodynamics is recovered from statistical mechanics. And well, um, since the mathematics of classical theories is well known and understood, physicists take them and construct the mathematics of the quantum theory from them. And this is what we call the canonical quantization. So the programs of quantization basically start, all of them start like this. We take the classical system and we look a way to promote them to operators acting on a Hilbert space, and which coincides with the description of quantum mechanics that we have currently. And well, uh, if we start with the Hamiltonian system, which defines a classical system, we got a symplectic manifold, which happens to be the cotangent model of the configuration space. This manifold is called the phase space, the famous phase space. Um, we have a symplectic form defining the manifold and a Hamiltonian vector field, which is defined through the Hamiltonian, also called the energy function, which induces the Hamiltonian in this way. So the Darboux theorem guarantees that we can write the symplectic form in these local coordinates of Q and P, and we end up having an expression for the vector field in this way, which of course has has f as integral curve only if it satisfies Hamilton's equations, right? So this function f is called the observable or a trajectory, right? So now by introducing the Poisson bracket, because let's remember that Poisson manifolds, which are basically manifolds together with a Poisson structure, which is a Poisson bracket, um, are seen as generalization of symplectic manifolds. So whenever you have a symplectic manifold, you can always write them in terms of Poisson structures. So this is achieved by inducing a Poisson bracket using the symplectic form in this way, and now we can write the Hamiltonian vector field in terms of the Poisson bracket. And we can for sure rewrite or reframe the Hamilton's equations in terms of the Poisson structure, resulting in this equation here, which means that we can study the evolution in time of the dynamics of the particle by terms of the Hamiltonian. Okay, this is important because if we look at this equation, it surprisingly looks very similar to the Heisenberg picture of quantum mechanics. So here we have the evolution of the observables in the quantum system defined through the commutators of the quantum theory. So these commutators uh, are like taking the place of the Poisson structure. So um, we use this similarity, and actually it was Dirac who, by noticing this similarity, postulated the idea of quantizing classical observables by turning them into operators acting on a Hilbert space. So the idea is basically take, as I mentioned earlier, take the classical observables, which are functions acting on the manifold, and promote them in some sense to operators acting on a Hilbert space. So basically, Dirac was postulating the idea of this map, which is taking the function into operator. And well, such mapping Q must satisfy what we now call the Dirac's axioms of quantization, which is linearity, the identity condition, the von Neumann rule, and the more like important or in more exclusive condition for quantization, which is the Dirac's quantization condition. So it's basically mapping the Poisson bracket to the commutators in the quantum theory. So this condition, it's one of the more strong ones. That's what I want to say. It's one of the more restrictive. And well, we also have irreducibility. Well, um, these actions, of course, have the intention of provide a method to quantize any observable f while capturing the more trivial quantization of q and p, which turn to be such that, as we know, the commutative relation of q and p as operators is just I h bar. And if we, I mean, the intention of these actions is postulated by Dirac is to give a method to quantize any observable and in the same process capturing the already trivial quantization the of the position and moment. So the operator corresponding to the position operator, it's basically just a multiplication by q, and the operator for the momenta is the widely known derivative over the position. And well, if we can write the action over the functions in this way, and these functions, which are complex functions, are acting on the space of a square integral functions, which happens to be the Hilbert space that I mentioned earlier. And well, following this line of thought, the quantization of the Hamiltonian in quantum mechanics will be like this. And well, how do we find the quantization of general observable? That's like the big question. Like, how do we find the quantization of a general observable over the manifold? If, if following the von Neumann rule, which is the rule of like the quantization of the composition function is the composition of the quantization. Um, if we do that for f composed with q and with p analogously, we like found these relations, and basically it tells us that we can quantize any function f depending linearly on p or q by quantizing each term of the Taylor expansion. So if it happens that you have a function that can be written linearly depending on p and q exclusively, like a polynomial, for example, you can quantize the entire function, quantizing term by term, right? Quantizing the q, substituting by this multiplication, and quantizing each p, substituting by the partial derivative of the over the position. And this basically leaves us the problem of finding the largest set of observables that can be quantized, and a map that takes functions to operators such that the axioms are satisfied. And well, what are the quantum problems? This description that I just gave about the quantization process, it's basically canonical quantization, right? So, nevertheless, it's widely known that Dirac's axioms of quantization are incompatible, and furthermore, generalizing this problem to any symplectic manifold is in fact impossible. This was proved by Groenewald and Van Hove. And well, take for example a function that includes PQ, which is a cross term. So rewriting, we basically have just take the binomial square, clear for PQ, and you will end up with this expression. And then you basically can canonically quantize by turning the p's into the p hat and q into the q hat, let's say. So it's basically quantizing term by term, as we said before. And by doing this, you end up with this expression. Okay, so this can be as I am writing because of the von Neumann rule, right? The composition of the quantization of the composition, and taking the square, we end up with this formula, yes, for the quantization of pq squared. And similarly, if we work with p squared q squared, the quantization using the same trick of taking the square and clearing, we now have this expression, which is different in nature, different from this other. It's not the same. So, in principle, pq squared, the quantization of pq squared due to the von Neumann rule should be and must be the same as the quantization of pq squared, right? The quantization of pq squared must be the same as the quantization of pq squared. But it's not the case. It's not the case, as you can see from the computation, yielding to a contradiction. And well, in short words, this is a straightforward example of the incompatibility of the axioms of quantization. And well, what we are going to do now is something I call canonical quantization done right, which is basically the first steps for geometric quantization. And well, given the fact it's actually proven impossible to quantize satisfying all the Dirac axioms, um, getting rid of some of the axioms or relax the conditions will be an attempt to establish a proper, but most importantly, doable program of quantization. Plus, we are going to seek only for a specific set of quantizable functions instead of all the smooth functions over the manifold. For instance, irreducibility and von Neumann rule won't be required anymore since they are the source of the illness shown in the previous example. Uh, this means that we are going to be concerned with finding a map Q, which throughout the whole talk I'll be using a lot the hat notation um, that you can find in the literature. So we are concerned with finding a map Q satisfying linearity, the identity condition, and Dirac's quantization condition. Um, and of course, we are looking for this set of observables and a Hilbert space. Um, well, preserving the Poisson bracket as the commutators make one think in the famous property of vector fields. So these vector fields satisfy this relation. Just remember that all Poisson brackets are also Lie brackets that satisfy the derivation rule. So uh, trying to guess a formula for quantization, we can just write the quantization of an observable f as the vector field induced by this same observable. So this is an attempt or first guess for a quantization formula. The problem is that if you substitute if equal 1, which is the identity function, it doesn't maps to the identity operator, okay? Because the vector field induced by a constant is 0. And well, we're not getting the identity function mapped to the identity operator, but it's possible to easily correct this by adding the original function, because if the vector field happens to be 0, if you just add the original function, you will get 0 plus 1 and you get the identity. And well, but now Now, with this second attempt for a formula of quantization, if you calculate the commutator using this new formula after the computation, you see that it doesn't respect Dirac conditions anymore. You are left with a leftover term, which is a Poisson bracket. And well, however, uh, like keep it up with this program of finding the quantization formula. If we choose a symplectic potential, which is a tautological one from on the phase space, if we choose a symplectic potential, um, if it's such that it has the property that its exterior derivative is equal to the symplectic form of the phase space, you can like check out that it satisfies this condition, and because of this we can add it to the quantization formula in order to fix the leftover term, and we can recover Dirac's condition of quantization. So now with this formula it yields to a quantization formula that satisfies the three axioms that we stated at the beginning for geometric quantization. And now it's time to check it out. Quantize Q and P, and after the computation, it results in these formulas as the quantization for the operators Q and P, the position and the momenta. The moment is fine. We have the known partial derivative of the over the positions, but in the case of the positions operator, we have the position. Remember that it must be just a multiplication by Q, but now you have a leftover term of a partial derivative on the momenta. So it apparently does not agree with the known operator for Q, but have in mind that this operator acts on functions depending only on the position, right? So this leftover term is going to vanish in all cases, and there is no problem. So if we assure that we are acting on function that depends only on the position, there will not be problem. And well, our problem now is that adding a symplectic potential raises the problem of unicity. I mean, remember that in the general setting of a symplectic manifold, you you don't have a global choice of coordinates, and it happens that locally you can choose different potentials in the same chart on the same subspace of the manifold, and in principle they can be totally different, um, while having its exterior derivative equal to the same symplectic form. So it's clear that the different or the second symplectic potential can be written in terms of the first one plus a function that can exist locally for some real function u, and which for instance will result in a different quantization, and that's a problem, because if you quantize using one symplectic potential, it yields to a quantization, but if you quantize using the other symplectic potential, it yields to a different quantization of the same function, which is something we don't want to happen. And well, if we calculate the difference of this symplectic potential, of course we're living with the du that we can rewrite as this. And rewriting like this make us notice that it exactly allows us to define a line bundle with transition functions, with exponential transition functions. And so the functions of the Hilbert space uh, that the operators act on can be seen or defined as sections of this line bundle, right? So we basically can write the action of the operators over the functions in the Hilbert space like this, and the action of the operator over the function It's finally using the formula written in this way. And if you manipulate the algebra here, you will notice that this expression is precisely the definition of a connection along the vector field xf. And you write it like this, and therefore we finally have a formula for the quantization of an observable f. And well, unfortunately, this isn't the end of the problem. Well, because we say that such a quantization recovers the primal operators q and p only if they act on functions which depend on q only, which is basically throwing off half of the variables. So this isn't trivial because in a general symplectic manifold we don't have a global choice of coordinates, as I was mentioning, and one way to guarantee to throw away half of the variables, you basically don't want them to mix them. That's why I say half of the variables, because you don't want the p's to be mixed with the q's. So if you select a specific subspace of the manifold and you impose this condition of over the symplectic form, you are sure that you're having the same type of vectors, right? And the space bounded by these vectors is half dimensional, and it's called, actually has a name, it's called the Lagrangian subspace. So we then choose a Lagrangian subspace for each point on the tangent space, and we need it to depend smoothly, but we also require it to be integrable. So basically we are choosing an integrable Lagrangian distribution because we are doing this for each point. So we have an integrable Lagrangian subdistribution P, which is often referred as the polarization. So we are really trying hard to fix the quantization formula. Um, and now that we already choose a symplectic potential, we are now with the problem of choosing a polarization. And well, the big news is that even after all this machinery applied to fix the quantization formula for any observable, by choosing a given polarization, we are only able to quantize linearly in either Q or P, meaning that, for example, no quantization of harmonic oscillator or not kinetic energy, because you gonna like choose of quantizing in Q or P. So you don't have those quantization for relative to the same choice of polarization. And well, uh, geometric quantization has is a subject study deep in mathematics, and it actually has some things to do in the theory of topological quantum field theory. That's something we can talk later. Uh, but from the physics perspective, it's actually not going in the quantization program anymore. So it's interesting as a mathematical development for geometry, but it's as the years have passed, it's getting like more away from the original intention of physics, right? And well, now let's move on to another very popular quantization scheme, uh, which is the deformation quantization. Yes, here we were relaxing Dirac's quantization condition by requesting that the Poisson bracket is not mapped exactly to the commutator, but you have other terms which are power series on the H bar. So the motivation for this framework comes from the integral representation of unitary operators. For instance, an observable can be written in this sense. Well, these points over here should be dot products. That's my bad. Well, so for any alpha on the Rn, its quantum operator will be like this. Will be written like this. Let me repeat this: these dots over. It's not derivatives. They are not derivatives. They are dot products. Okay. So now these functions can be expanded via Fourier transforms, and using this setting of like representing the observable as a Fourier transform, you can postulate quantization in such a way. Okay, and well, it turns out that the composition of this new WF formula for quantization, if you compose them, it acts in this way, giving place to a product that after doing the computations, you realize it includes the Poisson bracket. And actually, doing this final computation of the product F, the product G minus G, the product F, gives you exactly the new Dirac condition, let's say. So the idea basically is deforming the commutative algebra of observables in the manifold into a non-commutative algebra of operators using the associative but non-commutative product, this star product, let's say. And well, let if you let R be a ring and A an R algebra, you can have the ring of power series over T, and thus you end up with a moduli of power series in T with coefficients in A, which writes like this. Okay, so we are basically constructing the algebra of power series, which leads to the quantization, and thus we can define a deformation as the product. It's basically a linear function which behaves in this way, and one of the more recognized examples of a deformation is the so-called modal product. So by doing this, if you choose the standard manifold for a space, for a phase space, which is R to the 2n, um, you can calculate the Hamiltonian using the exponential representations like before, and you can show that it spans the same levels of energy that we usually do in physics. So this is a very famous scheme of quantization, and well, it leads me to one of the what I think is one of the a very important and relevant result in mathematics. So the idea of deformations of commutative algebras into non-commutative algebras, as uh, we like postulate in deformation quantization, has been explored from different perspectives, namely the deformation of commutative Poisson algebras into non-commutative operator algebras plays the ground for the application of a famous theorem from algebraic topology into our quantization program. So what I am presenting here is this theorem called the Gelfand duality, which basically tells you that from the structure of topological spaces, if you take the algebra of functions of a topological space, remember, and let's keep in mind that Poisson manifolds are, of course, topological spaces. So if you take the algebra of a topological space, you can, from the structure of the topological properties and the topological structure, you can uh, give place to a C-star algebra, and you can introduce using the pointwise uh, product over functions, which is commutative. You can construct a commutative C-star algebra, and you can do the opposite. You can start with a C-star algebra. You can like define the set of characters on the algebra, and you can recover the structure of a topological space just from the C-star algebra structure. And this this play in between topological spaces and C-star algebra is basically written in this theorem. This is what the theorem is trying to say. So it expresses a correspondence in between topological spaces and sister algebras. And this theorem allows them to make an identification in between topological properties and algebraic properties, as is shown in this table. And well, let's think for a moment. I mean, what is the importance of this theorem that maybe you can think it's coming out of nowhere? Well, it's relevant because it's about the stretched relationship in between topological spaces and system algebras. And if you think like this, from the topological point of view, generalizing a topological space, it doesn't seem trivial. I mean, if you want to do something more fundamental than a topological space, from the topological point of view, doesn't seem trivial. Nevertheless, from the algebraic point, remember that topological space correspond with commutative sister algebra. I mean, from the standpoint of sister algebra, you can just remove the commutative part, and now you are left with a non-commutative sister algebra. So the the exploration happens when you start studying non-commutative sister algebras and use the Gelfand duality theorem to explore what is in the topological point of view, which would be something that we can, in principle, call a non-commutative topological space, which are also called quantum groups. And it's not a random name. Uh, this is because these non-commutative spaces or non-commutative topological spaces are actually deformations of a space of algebras, of commutative algebras. So the deformation of, let's say, the algebra of a Poisson manifold, which describe classical mechanics, turns to be a commutative space which coincides with the description of quantum mechanics, meaning that you can say that the algebra of operators of quantum mechanics is the deformation of the algebra of functions in a Poisson manifold of classical mechanics, and is also a non-commutative space or quantum group that people, some mathematicians call quantum topological spaces. So that's the concept of quantum topological spaces. And um, of course, there is a lot to say about all this stuff. I'm not even close to be an expert. Um, I'll be leaving my information to the organizers if anyone wants to like have a talk with me or whatever. Here are the references. I encourage you to read this page and the like reference 1, 2 especially. Um, if you want to like explore more in detail what I exposed. And well, um, thank you for your attention. Um, and I hope you enjoy like hearing and listening about these things as much as I enjoyed writing about them. So well, thank you, and I'll be reading the comments.